This short mini-lecture introduces the classifications for chemical reactions and some common types of reactions that will be discussed in upcoming mini-lectures for this chapter. First, I'll introduce classifications for chemical reactions that indicate the way in which the atoms are rearranged in the reaction. Synthesis reactions, also known as combination reactions, occur when simple reactants combine to form a complex product, as indicated here by reactant A and reactant B coming together to form a bond, creating the molecule AB. This is the type of reaction that occurs when hydrogen gas and oxygen gas combine to make water, or when aluminum metal is oxidized by oxygen gas to form aluminum oxide, which is a common reaction type that takes place for most metals when exposed to oxygen gas. Decomposition reactions are basically the opposite of synthesis reactions and occur when a single reactant breaks down into less complex products, as indicated here by molecule AB from the first reaction now breaking apart to form separate A and B atoms. Running the water synthesis reaction from above in reverse gives the decomposition of water into hydrogen and oxygen gas. A very common decomposition reaction that you'll likely experience in lab this semester occurs when carbonic acid, H2CO3, is formed in aqueous solution. When carbonic acid is formed in water, it readily decomposes to water and CO2. This is important to remember, as whenever carbonic acid is produced in an aqueous reaction, chemists usually just write the products as water and CO2, as we know that the carbonic acid doesn't stick around for very long before it decomposes into these two products. This is often confirmed by the formation of bubbles during a reaction that forms carbonic acid, as the bubbles are generated by the carbon dioxide gas being formed. The next two classifications represent another pair with similarities. Single replacement or single displacement reactions occur when an element reacts with a compound and displaces one of the elements in that compound, as indicated here by element C switching places with element B in the AB compound. Double replacement reactions occur between two ionic compounds when the cations or anions switch places, as indicated here by B and D swapping places in the reactant compounds, forming two new product compounds, AD and CB. In this first example of a single replacement reaction, magnesium metal is replacing the copper ions in the copper sulfate ionic compound, and this forms a new magnesium sulfate compound and copper metal. In the second example, the displacement is a little harder to see because potassium solid is displacing a hydrogen in water to form potassium hydroxide and hydrogen gas. It helps to see the displacement in this reaction by remembering that water essentially contains a hydroxide ion bonded to a hydrogen ion. So if the hydrogen ion is displaced by the potassium, this is how we end up with potassium hydroxide. And if this happens twice with two potassium atoms and two water molecules, then the displaced hydrogen ions from each water molecule will then combine together to create the hydrogen molecule that's being produced in this reaction. In the next example of a double displacement reaction, the chlorine and fluorine anions swap places, creating two new ionic compounds as products, one of which is soluble, indicated by the aqueous state label, but the other of which is a solid and represents what we call a precipitate. Which brings us to the second set of reaction types, which are organized based on the types of reactants and products that are involved rather than the type of a rearrangement of atoms that occurs. For example, a precipitation reaction involves the creation of an ionic solid, often in aqueous solution, and often via a double displacement reaction like the last sample we saw on the previous slide. The solid precipitate forms when aqueous solutions of certain ions are mixed and favor the creation of an insoluble ionic compound. Solubility and aqueous solutions will be discussed more in the next mini-lecture. The next one, acid-base reactions, are often called neutralization reactions as they often involve acidic and basic solutions combining to give a neutral solution of mostly water and an aqueous salt. These reactions involve the exchange of a proton or hydrogen ion from the acid to the base. So we refer to acids as proton donors or hydrogen H plus donors, and bases as proton acceptors or H plus ion acceptors. Finally, oxidation reduction or redox reactions involve transfer of electrons between two chemical species, leading to a change in the oxidation states of the two species. This typically happens in synthesis, decomposition, and single replacement reactions, and we'll see how to identify oxidation states and when they change for certain chemical species in a future mini lecture. In fact, I've got several mini lectures planned for redox reactions as they're kind of the most complicated out of these three. There will be at least one separate mini lecture that addresses each of these three types of reactions, and it will become easier to identify these reaction types after we've learned more about how each one works. This concludes the second mini lecture for Chapter 8. Please note any questions you may have about this material and how it is utilized to solve problems in the suggested end of chapter exercises and the sapling homework for this chapter. Please post any urgent questions on Piazza. I will also take questions on this material during one of our required class meetings, and during that time we will focus more on problem solving for concepts in this chapter.